The majority of photons that rush toward a black hole are either softly diverted away or swallowed into its depths and never escape. However, a select handful avoid the hole by performing a series of sharp U-turns. Some of these photons continue to circle the black hole for what seems like an eternity. The ensuing ring of orbiting photons, which astrophysicists have dubbed a cosmic movie camera and an infinite light trap, is one of nature's strangest phenomena. The photon ring, which orbits the hole farther away, hasn't drawn much attention from theorists. In contrast to the black hole's iconic event horizon, the region where gravity is so intense that nothing can escape. Given that the event horizon represents the boundary of what is known about the universe, it makes reasonable that scholars have been fascinated with it. Gravity follows with spacetime curves throughout the majority of the cosmos, according to Albert Einstein's general theory of relativity. But within black holes, spacetime warps so drastically that general relativity no longer holds true. Therefore, many who study quantum gravity have looked to the horizon for solutions in their quest for a more accurate, quantum explanation of gravity. Recent research has shown that the photon ring surrounding a rotating black hole exhibits an unexpected sort of symmetry, or the ability to undergo transformation while maintaining its original form. The symmetry implies that the ring might contain data on the quantum makeup of the hole. Researchers are debating whether the photon ring might even be a component of a black hole's holographic twin, which is a quantum system that is identical to the black hole and can be thought of as the black hole emerging from like a hologram. Before scientists can definitively say whether or how the photon ring encodes a black hole's inner contents, a lot more theoretical research is required. The new work, however, provided a precise test for any quantum system claiming to be the black hole's holographic twin. The fact that the photon ring is actually visible, unlike the event horizon, adds to the excitement around it. The formation of the photon ring seems to be a universal effect that happens around all black holes. Theorists concluded that the sharp line of the photon ring provides direct information about the black hole's characteristics, including its mass and amount of spin, in contrast to the whirlwind of violent colliding particles and fields that surrounds black holes. We would see a single ring of light if a single photon performed a single U-turn around a black hole before accelerating toward Earth. Two U-turning photons appear as a thinner, more ethereal subring within the main ring. Additionally, photons that perform 3 U-turns appear as a subring within another subring, and so on, forming nested rings that are each progressively thinner and fainter. A succession of time-delayed images of the surrounding cosmos are produced as a result of the fact that light from the inner subrings has made more orbits and was thus recorded before light from the outer subrings. The collection of subrings, which together resemble movie frames and document the history of the visible universe as seen from the black hole. The scientists came to the conclusion that the ring's circular structure suggests a class of symmetries known as conformal symmetry. Scale invariance, or the property of having the same appearance whether you zoom in or out, is a property of conformal symmetric systems. Each photon subring in this instance is a precise replica of the one before it. A conformally symmetric system also maintains its original shape when all spatial coordinates are inverted, shifted, and then inverted once more, as well as when time is moved forward or backward. Scientists discovered a fresh technique to link general relativity to the quantum world, at least inside black holes, by carefully examining the specifics of this symmetry. They envisioned removing the black hole and substituting its event horizon with a surface that contained a quantum system of particles that adhered to conformal symmetry, which they referred to as a holographic plate. They established a correspondence between the system's characteristics and those of the black hole, as if the latter were a higher-dimensional hologram of the conformal quantum system. In doing so, They created a link between a black hole's general relativity description and its quantum mechanical description. Starting from the description of spinning black holes in general relativity, called the Kerr metric, scientists began to look for hints of conformal symmetry. They visualized hammering the dark hole till it rang like a bell. Similar to gravitational waves produced when two black holes collide, these gradually fading vibrations are waves in space. Similar to how the ringing tones of a bell rely on the shape of the bell, the black hole will vibrate at some resonant frequencies that depend on the shape of spacetime or Kerr metric. The Kerr metric is extremely intricate, making it impossible to determine the precise pattern of vibrations. By solely taking into account high-frequency vibrations, which are the result of very severe impacts with the black hole, the researchers were able to approximate the pattern. They discovered a connection between the structure of the black hole's photon rings and the wave pattern at this high energy. The photon ring turns out to be entirely governing the pattern. This connection between the black hole vibrations and the photon rings may be a harbinger of holography. These results suggest that a natural candidate for a portion of the holographic plate of a rotating black hole is the photon ring, not the event horizon. If so, there might be a fresh approach to think about the black hole information paradox, a long-standing puzzle that involves what happens to data about objects that fall into black holes. Recent estimates suggest that the universe somehow keeps this information safe as a black hole slowly evaporates.